Oh wow, big sound. Big sound. Yeah.
Well, now it's
It'll
recording.
be.
Now it is recording?
Yeah.
Are you recording the recording?
Yeah.
Okay, that's too deep for me.
Yes.
So the camera is now recording again?
Yes.
Yeah, okay, well, we're going to remember this every freaking time. And I thought the hardest part of my day was going to be when, like, the button came off my pants this morning on the way to school. No, I was just afraid it came off, so I had buttonless on my pants. Anyway, but that's apparently not the big thing for me to worry about. All right, friends, let's do it. Another one. So not geometric. Let's just assume it's not geometric. All right, so if f of x is 1 over x times the natural log of x, I need to be convinced of all the things. For x greater than or equal to 1, x greater than 1.
Greater than.
Let's make it 2.
Okay, that makes a lot.
Okay. For x greater than or equal to 2, what are the things?
It has to be. The function has to be continuous, positive, and.
Okay, continuous. Now I might want to stop here. X times the natural log of x can be equal to 0.
Yeah.
But that happens if x equals 0 or the natural log of x is equal to 0. Natural log of x is equal to 0 only if x is equal to 1. Which is why I need to pick something 2 or bigger. Okay? So are we okay? Continuous for x greater than 2? Continuous for x greater than or equal to 2. Check. Next thing. Positive. Is this guy positive? X times the natural log of x. The graph of the natural log of x is positive after 1. This guy's positive. X is positive. 1 over positive is positive. Check. Decreasing. You might want to argue, well, f of x is increasing. The graph of natural log of x is increasing. So what must be true is that x times the natural log of x is increasing. So 1 over x times the natural log of x is decreasing. We've picked a function that is continuous, positive, decreasing. Lewis?
What if one of them doesn't apply, like if it's not positive, they use Dr. from there?
Oh, thank you for asking that. What if it wasn't positive? Can't use the integral test. So these three things together mean the integral test can be used. All right, so let's do it. The integral test can be used. So we go over here and we look at the integral from 2 to infinity of 1 over x times the natural log of x dx. You know exactly what we're going to do next. We're going to integrate. We're going to try substitution. And the substitution that we're going to do here is we're actually going to let u equal the natural log of x because du dx is 1 over x, so du is 1 over x dx. What that means is that my integral is now 1 over u du. The x value is 2, so the lower limit is the natural log of 2. My upper limit is infinity. The natural log of infinity is infinity. I need to integrate the integral of 1 over u. Natural log of the absolute value of u from the natural log of 2 to infinity. We plug in natural log of infinity minus the natural log of the natural log of 2. Natural log of infinity is infinity. Minus the natural log of the natural log of 2, you know what that is. Infinity minus the natural log of the natural log of 2 is infinity. Therefore, diverges. The integral diverges. What we really care about, though, what we really deeply care about isn't the integral. You go back to the series. Therefore, the integral from, oh my God, I did it again. The sum from 2 to infinity of 1 over the n times the natural log of n diverges by the integral test. Okay. It's really going to be the same process. It's a long process. It is not a quick and easy you're in and you're out. These are really long problems. Don't expect them to show up much in the multiple choice part of the test. I don't think I can do this in 2 minutes. And that's about the pace you need to be working when it comes to the multiple choice. There are, oh, okay. You worried me. I was like, oh God, now what?
I was just zooming in.
There are, however, some that are quick. There are some quickies here. And this is what's called the P-series test. We've got about 10 minutes, which is just enough time for me to introduce you guys to the P-series. P-series are a special series that you are going to love because they are, oh my God, so quick. So quick. First of all, our definition of a P-series is a series that is expressed this way. It's 1 over n, right? Your term number is getting raised to the p power. The p is constant, right? Just like, you know, good, healthy people, your p is constant. Hi, Mr. Link.
That's a good time.
There you go. His p is constant too. So the integral from 1 to infinity, 1 over n to the p is considered a P-series. And P-series behave in very predictable ways. What we're going to do is we're going to look at a couple of special ones. For example, if P is equal to 1. If P is equal to 1, then your series is the sum from 1 to infinity of 1 over n, which would be 1 plus a half, plus a third, plus a fourth, plus a fifth. This is called the harmonic series. This is the only one that has a name that you need to worry about. It's the harmonic series. You're going to see the harmonic series a lot. What I want to do is I want to determine, does the harmonic series converge or diverge? So I want to know, does this series converge or diverge? How would we ever determine convergence or divergence of a series? Is it geometric? Geometric always have that form. It's a times the ratio to the nth power. Not geometric. It's not telescoping. We don't have the subtraction of 2 fractions happening there. So there's one thing left in the toolbox right now. The integral test. Okay? If we're going to use the integral test, let's run through it. F of x is 1 over x. If I look at 1 over x for x greater than or equal to 1, does it satisfy all the conditions? Positive. 1 over x positive? For x greater than or equal to 1? Absolutely positive. Check. Other thing? Continuous. Is it continuous?
Yes.
Right? You know what that graph looks like. It's the boomerangs. It's continuous for x greater than or equal to 1. This is the thing. Positive, continuous, the last piece? Decreasing. Is that true?
Yes.
Absolutely. All the things, guess what? Use the integral test. So by the integral test, that means we're going to look at the integral from 1 to infinity of 1 over x dx. Take like 30 seconds, finish that off. You know how this one ends. Infinity, natural log of infinity, natural log of 1, natural log of infinity, infinity, natural log of 1 is 0, we get infinity. Our conclusion? Diverges. The integral diverges. So Lewis, what's really your conclusion? We just showed the integral diverges. What's the conclusion though? What's the thing that we really care about? The series diverges. So specifically, the harmonic series, which is this guy over here, the integral, I kept saying the integral, the sum, diverges. So the good news is, for those of you that are really good at memorizing things, as soon as you see harmonic, diverges. Don't do any other work. State that it's harmonic, get out of it. Try the next one. So p is equal to 2, so now you're integrating 1 over n squared. X is 1 over x squared, and that is positive. It is continuous. It is decreasing. Is everybody feeling like really good with the criteria? And really, for one like this, just convince yourself. You just got to indicate, yes, I checked positive, yes, I checked continuous, yes, I checked decreasing. On the multiple choice, don't bother. Okay, integral from 1 to infinity of 1 over x squared dx. I need to be able to integrate 1 over x squared. Integral 1 over x squared is really the same as x to the negative 2 dx from 1 to infinity. So is that negative 1 over x? From 1 to infinity, that's negative 1 over infinity minus negative 1 over 1. Negative 1 over infinity. Bottom gets big. Right, this guy's going to approach 0. Minus negative 1. What you get is converge. Is everybody okay with converges? Your conclusion then?
The series converges.
The series, this is the thing that I care about. This guy converges. 1 to infinity, 1 over n squared converges. Now, the really neat thing is this last one. Tract equals a half. And then we'll bring all the results together. Stephen, if I'm over here, can they see? So 1 over n to the half from 1 to infinity, my function is 1 over x to the half. Maybe you want to write it as 1 over the square root of x, and just run through the things again. Positive, continuous, decreasing, check, 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 check. Positive, continuous, decreasing, integral test applies. Well, if the integral test applies, I integrate 1 over the square root of x dx from 1 to infinity. The integral of 1 over the square root of x, maybe you're better off writing it as x to the negative 1/2 dx. From 1 to infinity, add 1 to the power, divide by the new power, and what you're going to get is 2 times x to the half from 1 to infinity. Plug in infinity, you're going to have 2 times square root of infinity minus 2 times the square root of 1, square root of infinity, you guessed it, infinity. diverges your conclusion. Series, this guy over here, 1 over n to the 1/2 diverges by the integral test. How's everybody feeling? Mostly okay? It's a process. You're going to follow the process. Is the function continuous, decreasing, positive, right? Does it satisfy all those? Then you get to use the integral test, then you integrate. What's nice about the P-series, though, is this. The harmonic series diverges. We tested if P is equal to 2, and if P is equal to 2, it converged. Anytime P is greater than 1, the harmonics, the P-series will do the same thing. It'll converge. Anytime the p-value is less than 1, it'll diverge. The harmonic series is that borderline case. We're going to talk more about this tomorrow. Anybody who needs help, I'll be available during lunch, where I'm hopefully figuring out how to replace the button on my pants and splice all these videos together. We've got part on camera, we've got part on phone, and then we've got part on camera. It's just delightful. None of it's secret fault, though.
There's too much going on there.
All right, Mr. Link, do you need time for announcements or?